Good morning to all, and thank you for taking the time and participating in this webinar entitled Trust PV, Advanced Monitoring and Aerial Inspection. This webinar is one of a series organized by SolarPower Europe in the framework of the Trust PV project, funded by the Horizon 2020 program. My name is Guillermo Oviedo Hernandez. I'm a Technical Innovation Manager and R&D Team Leader in BayWa RE Operation Services. I'm part of the Trust PV project. The objective of this webinar and the series of these webinars is to disseminate the results achieved in these 4 years of research within the Trust PV project, and to give you a flavor of what we have been doing in this collaborative effort. The Trust PV project is a big consortium of 20 partners, a mix of private companies and research institutions, with the goal of improving the performance and reliability of solar PV plants. Next slide, please. So let me present the speakers of today. Lucas Küste holds a Master in Physics and soon a PhD in Energy Science at the Politecnico of Milan. He works at the Institute for Renewable Energy at Europe Research in the field of performance and reliability of PV modules. Marco Berliocchi holds a PhD in Electronic Engineering. He is the founder and CEO of Raptech, a company at the forefront of the clean tech industry, focusing on innovative digital solutions in renewable energy for monitoring and asset management. He considers himself an ardent advocate of sustainable technologies and has dedicated his career to advancing digital solutions for the energy transition. After these two presentations, we'll have a Q&A session of about 20 minutes. And before passing the word to the speakers, I'd like to remind the audience to input the questions, comments in the chat box, and we will go through them at the end of the two presentations. So now I give the word to Lucas.
Yes, good morning, everyone. Thank you, Guillermo, for the introduction. I'm happy to share with you today the developments, the results in Trust PV on three different inspection techniques, which are electroluminescence, daylight photoluminescence, and ultraviolet fluorescence. I will present all three techniques in different chapters, but we'll start with an introduction, why we actually looked into further developing these inspection techniques. You see here all the partners from Trust PV in the presented developments, mainly Huawei, Above, and Europe Research were involved. We start with introduction. So large-scale photovoltaic inspection, how is it actually done? Therefore, we have a look into what the operation and maintenance best practice guidelines published by SolarPower Europe say. And they say that you should do a yearly, or they suggest to do a yearly infrared inspection of the whole PV plant. And then if you detect a hotspot, to do electroluminescence inspection for root cause analysis of the PV modules with hotspots. This raises the question, why not doing electroluminescence inspection of the entire photovoltaic system immediately? And it's quite easy to answer. It's a cost-benefit consideration. So on the one hand, you have the costs to perform an inspection technique. And then on the other hand, the benefit is the outcome, so the detectability, what defects you can detect. To show this, we developed this matrix within the TrustPV framework, which shows, on the one hand, all different typical defects which can occur in a PV module, and then on the other hand, which inspection techniques are able to detect this defect. And if we look now at the comparison of infrared techniques, which is shown here by the yellow frame, and luminescence technique, electroluminescence, is shown by the blue frame, and daylight photoluminescence by the green frame, we see that infrared thermography actually shows quite a lot of defects. But if we go now to the second step of root cause analysis, we have to eliminate a few because they are just shown as hotspots and cannot be, or the root cause of the defect cannot be identified. Therefore, we see that electroluminescence has a huge advantage above infrared thermography, at least in the detectability. That's why it's used for the root cause analysis. On the contrary, if we look now at the costs of an inspection method, they depend mainly on the speed in inspecting a certain size of a PV system. So how fast can we detect a certain capacity, installed capacity, a certain amount of installed capacity within a time frame, so kilowatt peak per hour. For infrared, there's commonly reported between 1 and 4 megawatt peak per hour. For electroluminescence, maximum of around 750 kilowatt peak per hour is achieved, and photoluminescence around 300. Daylight photoluminescence being a very new technique, there is not really anything reported yet. Therefore, in TrustPV, that means slower inspection technique for electroluminescence and or inspection speed for electroluminescence and photoluminescence causes higher costs, obviously. So in TrustPV, we made use of the combination of different stakeholders along the whole value chain of the PV project to improve these two inspection methods for having a more detailed results from inspecting a PV plant than in what infrared offers. We start with electroluminescence. I will present quickly the principle behind. It's quite simple. For electroluminescence, we inject the current into the PV module, or in large scale PV plants into the PV module string, and the cells act like LEDs, so they emit light. It is the luminescence light in the near infrared regime. And this light depends on the properties of the cells, and therefore we can see many defects in high detail, as you can see here, cell cracks. These are backsheet scratches, but they also allow to show some properties of the cells like series resistance and more. The drawback for electroluminescence inspection is first that it has to be performed during the night, and second that you need to connect a power supply to the individual PV module strings in the PV plant to allow to inject the current. This is a time-consuming process and therefore a limiting factor for to perform fast aerial electroluminescence inspection. In fact, the power supply connection is reported to be about 20 to 50% of the total inspection time. So half of the time is just moving the power supply from string to string. And that's where we wanted to adjust. So we used an electroluminescence ready inverter prototype, which was provided by Huawei. And this inverter allows to take the power directly from the grid and inject it into the connected PV module strings. The MPPTs of the inverter are individually selectable, so you can go string by string for current injection. This is a test plant of TrustPV here at Europe Research in Bolzano in Italy. And you see how the inverter, which is installed here at this test plant, injects current into all the modules connected. And then you can go around and do your electroluminescence inspection. we looked into some further aspects about electroluminescence and the electroluminescence ready inverter, which are the power limitations of the inverter and how they affect the PV plant layout planning. So the power limitations are that the inverter has a minimum and maximum voltage and minimum and maximum current in which it can operate the current or the backpowering, so the electroluminescence functionality. As the voltage of the PV module depends on the temperature, it is possible that with different temperature, you might move out of this inspection window, and therefore, if you want to apply short circuit current and the temperature changes, you might not be able to do that. Therefore, we did an analysis on the temperature behavior of the PV modules and also on how this temperature changes during an electroluminescence inspection itself, as current injection increases the temperature of the cells. The results of this, I have to ask you to follow this QR code to the article where they are presented, because they don't fit into this presentation. Then to do fast imaging, we applied the electroluminescence method on aerial vehicles, so on drones. This was done by above. There you can see that the camera, an indium gallium arsenide camera, needed for fast imaging in the shortwave infrared regime, and the mini PC is mounted as payload on the drone. For a test, they created a manual flight plan for a test plant. They controlled the drone height, via this remote control, and then with the camera and the mini PC on the drone, they did the test flight. And ideally, we would have liked to backpower for the test flight with a Huawei inverter. Unfortunately, because the tests were done in the UK and this inverter prototype is here in Italy, we couldn't do that. We used a normal power supply instead to do the first tests. The images are downloaded from the camera after the flight and then processed. And here you see the camera or the test in action, the drone flying over the PV module array, and on the bottom right in the overlaid video, there's the footage from the electroluminescence camera. And you see already some defects. If we look at the PV modules here, we see that it nicely shows some delaminated bus bars in some cells, and also some micro cracks are visible. Now I move towards the next topic, which is daylight photoluminescence, which shifts the imaging towards the day, but it remains with the same detail of images. So first, again, the principle of standard photoluminescence. The carriers inside the cells are excited by illumination, and then they are forced to recombine by keeping the PV module in open circuit operating point. So we run the module at open circuit instead of maximum power point, and therefore the carriers recombine and emit the luminescence signal, which is the same as the electroluminescence signal. So therefore we see also similar results. Standard photoluminescence is typically done during the night. For daylight photoluminescence, we use instead the sun as excitation source. And that comes with a challenge of separating the luminescence signal from the strong sunlight. It is done by recording two images. So a second image at a high current state, here point A. And then we have the image taken with the luminescence signal, and in high current, the carriers don't recombine, and therefore we have an image without the luminescence signal, which we can then subtract from the first, and that leaves us with only the luminescence signal emitted, and therefore our daylight photoluminescence image. The advantages are, again, that we have the high detectability of many defects. It's comparable to electroluminescence, and it is performed during the day, and we don't have to inject current. The drawbacks are that for a good signal to noise ratio, we actually need not just one image pair, but we need several images of each operating point to average the image to get a higher signal and reduce the noise. And then to do this, to record all these images for large PV plant inspection, to have a seamless image acquisition, we need to switch the operating point of the PV module all the time between open circuit and high current, so that when we fly with the drone, we actually can record all the images. And this brings us to the second development, which is the daylight photoluminescence ready inverter, where we can choose 2 operating points for all the connected PV modules, again, string-wise, and then activate the daylight photoluminescence functionality, and the PV modules toggle between the 2 points set. Here again, we are in the test area with the camera mounted on a large tripod, and then when we activate the functionality, you see here that the inverter switches the operating points, and for the different operating points, we have the signal emission activated and deactivated. As a result, we see here on the bottom the daylight photoluminescence images of 2 modules, and as comparison, electroluminescence images of the same modules above. And you see that there are similar defects, or the defects visible, or the results in general are very similar. We see some mismatch between cells. We see here the handling points from production, most probably. We can see here cell cracks. Also, I have to say that the electroluminescence images are recorded not outdoor, but indoor under controlled conditions, while the daylight photoluminescence images are obviously recorded outdoor using the sun. Some further work on daylight photoluminescence we did shortly shown here. Again, I ask you to refer to the article if you are interested in that, or contact me later. This further work we did first is, well, to perform the subtraction of the images for daylight photoluminescence, we have to know at which operating point an image was taken. So if it is open circuit or high current state. This can be done by synchronizing the camera with the inverter, which again is difficult for large scale inspections where you have many different inverter and also the camera mounted on the drone, and you fly and you switch, or you move from one inverter to the other. Therefore, we developed the operating point detection algorithm, which allows to detect the operating point of an image after it was taken by comparing the intensity in the image with others. Another investigation we did is on detecting the or underperforming PV modules by daylight photoluminescence by comparing the signal intensity. And you see here that there's a nice overlap for the cell voltage with the luminescent signal, and so that allows to detect underperforming PV modules. Again, for more details, I have to ask you to refer to the article. So to show you the improvements due to these developments I just presented, I refer back to the table of inspection speeds. And here you can see now the developments due to the improvements in truss PV. And as I said, the inspection or the connection of the power supply in electroluminescence takes 20 to 50% of the time. Therefore, if we reduce this to 0 because we use the electroluminescence ready inverter, we increase the inspection speed by 40 to 100%. And therefore, we can gain a maximum of 1,500 kilowatt peaks per hour inspection speed. For daylight photoluminescence, as we couldn't do a UAV, so a drone flight or a drone inspection yet, we had to estimate the time recording for one module takes, and then the drone speed and the PV plant layout, and we came up with an value of 1,200 kilowatt peak per hour for the inspection speed with daylight photoluminescence. So therefore, with these improvements, we are getting in the range of infrared thermography, and that makes these luminescence techniques, at least compatible with more compatible with infrared thermography. Finally, I would like to talk about the application of ultraviolet fluorescence on aerial vehicles. Again, shortly, the principle. Fluorophores, the PV module is illuminated with UV light, which then triggers a fluorescent signal, as you can see here, the blue signal on the right-hand side. The intensity of the signal depends on the number of fluorophores in the encapsulation material. And these fluorophores build up, so the number increases due to long-time sun exposures, so the UV load, which is employed to the encapsulation material over time. They decrease due to photobleaching. Photobleaching happens if oxygen is present, and the oxygen in the PV module comes through the backsheet into the encapsulation material, but then to the front side, from where we are recording the signal, the front side, it reaches only through the cell gaps. So you see here on the bottom, quite homogeneous signal above the cell, but then this frame of no signal, at the frame or at the corners, and this is because the oxygen can move through the cell gaps to the front encapsulation material. Here you see, quite not so homogeneous signal. This is due to cell cracks or strongly cracked cell, and then the oxygen can also transmit through the cell cracks to the front encapsulation material and reduces the signal. This also shows the advantage of ultraviolet fluorescence. It can detect cell cracks, and this with the temporary resolution, because the signal doesn't vanish immediately, but it takes some time. So you can estimate at what time the cell cracks appeared. The drawbacks for ultraviolet fluorescence are that it is performed during the night, and that the encapsulation so the encapsulant must develop fluorophores, and that depends a bit on the composition of the encapsulation material. And finally, photobleaching only happens if oxygen is present, and in glass modules, oxygen cannot transmit through the backsheet because there is no backsheet. Nevertheless, we did again a test with doing ultraviolet fluorescence from a drone. This was again done by above. They created again for this test flight a manual flight plan, and on the drone there is a 100-watt UV light source and a compact camera with which is fitted with a UV high pass filter, and on a gimbal. And with this, then they fly over the PV modules, they shine the UV light onto the modules, and the fluorescent light is recorded, which gives the results, which are again downloaded and processed after the flight. Here you see the results, or some results of the tests performed at the PV site in the UK. And you see nicely that on the diagonal lines, these are cell cracks, and the horizontal lines are the bus bars. And if we compare the images with infrared images, we also see that cells which are hotter actually show a stronger UV signal, which is in line with the literature. Finally, I want to talk about some steps which are still missing. As I said before, we couldn't do yet daylight photoluminescence from drones. That will be demonstrated this summer, and we're looking forward for that. And then finally, we also have to continue in the last month a bit into looking in looking into the post-processing steps for all the presented methods to optimize them and to go for automated defect detection and analysis of performance degradation. And with this, I want to thank you, and please, contact me if you have more questions. I know there were a lot of topics and a lot of information in a short time.
Thank you, Lucas. Great work summarizing all of this work. I can see already some questions coming in, but for the sake of timekeeping, I will keep them at the end. So let's thank you again, Lucas, for his great presentation, and let's move on to the next one. So Marco, the floor is yours.
Hello, hi everybody. Thank you for joining us in this webinar. So I'm going to talk about to give you a big picture about innovative wireless technologies for PV monitoring. We worked on these topics within the Trust PV project. When we started almost 4 years ago, the narrowband IoT protocol was just released, and the 5G was still pretty new. Now the things are changing, so the 5G is much more common now. So we wanted to see on the market what we could find on the two different aspects of the system. So taking care of the communication part, so looking for connection providers, and taking care of the hardware part, the device part, let me say, including sensors, and eventually devices that could offer all integrated in just one device. So we contacted all the suppliers. We selected the best solutions in our opinion. We bought the devices and we started testing them in lab in a first phase. We changed the integration. The first thing that we noticed that not a lot of devices could offer already integrated the communication technology. So we had to do that using the converters, as I will show you later. And then final step was to test in real life conditions. So it means on PV installation. And at the end, we wrote down some conclusion and some observation in our final reports that you can download in the Trust PV website. Here I reported a direct link. We produced two different reports, one more general regarding all kind of sensors, and the other one more focused on module level monitoring. That is the extreme application of Internet of Things at the PV system. It means that each photovoltaic module can send data regarding its own voltage, current, and temperature. So let's talk in general a bit about Internet of Things. With this name, we cover all the technologies that permits an exchange of data between devices, sensors, directly to the cloud. Now, it's an approach that is becoming more and more common, especially for monitoring applications such as road lighting, parking, metering, traffic control, smart agriculture. That is an hot topic in the photovoltaic sector as well. These technologies need some special requirements, such as long ranges, high coverage, good signal penetration. This is a very important one, and low energy consumption. Regarding the peak rate, it depends. In a lot of application, that are not real-time critical system, we don't need a very high peak rate. All these kind of technology that fulfill these requirements are called grouped in a bigger family called low-power wide area networks. Some of them are already used in PV sector. Sometimes we found LoRa, Sigfox, Zigbee, or Wi-Fi already working. But yeah, we wanted to focus on these two new technologies. During the first year of our work, the narrowband IoT has been put under the same standard of the 5G. So now it's a branch of the bigger standard. And they have quite a different application. 5G, for instance, is more focused on enhanced mobile broadband. So it means that can be used for broadcasting, media delivery, or online gaming, and for ultra reliable low latency communication. It means that in this case you need the real time because it's used for augmented reality, for remote control, for motion control, for robots. On the other hand, narrowband IoT has some different skills because this protocol is more used for massive mobile type communication. It means that it can be used for actuators, sensor, and for wearables, for instance. They are both cellular technologies. This is pretty important because it means that they don't need the gateway, as we see later. Narrowband, as the name says, is more for Internet of Things, and it offers all the main characteristics that an Internet of Things system should have. So it is low cost. It has a very good penetration indoors and underground, and it's a protocol that can manage hundreds of thousands of devices per cell. Here we wanted just to compare the main wireless technologies and highlighted the characteristics that, in my opinion, are the most important for narrowband 5G. The first one is that they are international standards. It's very important for their diffusion. The 5G is a very high peak data rate. It's about 10 gigabit per second, and a very low latency time. So it means that it can be used for real-time critical application. Narrowband, on the other hand, has a very good signal penetration. So we tested that it's very reliable used inside the inverter cabinet or in area where the coverage is not that good. And that makes a great sense in the PV installation that are usually in the countryside. And then a very important one as well, in my opinion, is that they are cellular technologies. So it means they don't need a gateway at all. So this is important because you have less devices and you have a direct connection to the cloud. So the most common architecture that you can find in a PV system is obviously the wired architecture. It means that each sensor is connected directly to a central data logger gateway that it's usually installed in the inverter cabinet. So it means that you have all this data network composed by cables that goes from the weather station, from the meters, from the inverter, from the string box, from the trackers, and they go to the data logger gateway. The most common protocol used in this kind of application is the Modbus protocol. On the other hand, the IoT architecture changes a bit the things, because in this case, each sensor is connected directly to the cloud to store data in a remote database. In this case, each sensor is equipped with a communication module, a wireless communication module. And so, as you can see, there is an intrinsic redundancy in the connections. It makes this kind of systems much more robust than the wired ones, because if you have a failure in one communication module, you still, it means that probably you will lose data coming from the weather station, for instance, but you will still have all the information regarding all the other sensors. So that could help, because I mean, it can happen that the connection in the field is not good, or you can lose it. In this way, you can avoid lack in the data acquisition. To see if the narrowband IoT could be a real good option for communication in a PV installation, we studied together with the TREE, that is another partner of the project. We studied the amount of data exchanged from a standard PV plant. So we considered, for instance, 1 megawatt plant composed by 250 strings, 10 data loggers, 50 inverters, 1 weather station. We have seen that the amount of data exchanged per day is around 16 megabyte. That makes 6 gigabytes per year. And yeah, we verified that it fits with the offer of communication provider that we can find now on the market. Then we focused, as I said, on the module level monitoring systems. These systems are systems where you collect the data from the single module as well. We tested them in a big plant provided by Bariva. It was in the central part of Italy, around 20 megawatt of installed power. It covered 1 kilometer square of area, and it's interesting that it was located in presence of hills. So this is important because it could affect the stability of the connection. And the other tests have been done in the north of Italy at the UREC research facility. We tested 3 different architecture. The wired architecture, it means that the sensor connected on each panels are connected in series between them, using the power line communication to a string box reader. The data taken on each panel were temperature and voltage. The string box reader on the other side collected current, the total current, that is the same, and the string voltage as well. Then the string box reader is connected to a data logger and then to the web. We have seen that this configuration could present some issues because in the central part of the day, the current was very high, and the interference with the power line communication affected the quality of the data collected. We tried an hybrid IoT architecture as well. It means that we left the communication part between the different modules, still power line communication. And we use the converter to transfer data from the string box to the cloud. So we avoid a device, we avoid the gateway, and the cables between the exchange box reader and the inverter cabinet. In this case, we used a converter from the Modbus protocol to narrowband IoT protocol. Then the last architecture that we tested was a full IoT architecture. It means that each box, each sensor box installed on the back of the panels was equipped with a wireless module, a wireless modem, sending data directly to the cloud. In this case, the use of cabling was strongly reduced, so the installation was much easier. We had some issues as well on the data collection. In this case, we had the lack of data at the beginning of the day, at the end of the day, probably for some power supply problems. And so, yeah, we reached some conclusions. A part of them are related to the sensors themselves. So specifically to the module level sensors, we have seen that they are not still reliable to be used. We had a lot of issues on them. But if we want to consider just the communication part, we can say that the narrowband IoT is very good for standalone installation because it has low consumption. And so you can have standalone devices. We tested the temperature devices, irradiance devices, and they really work well. They are, in general, the architecture as seen is very reliable because you have an intrinsic redundancy of connections. And also the installation is much easier and the maintenance as well, because you have a very strong reduction of cables. And another aspect that we consider very positive is that the interference are reduced as well because the cables are reduced. So that's a very good side effect of using the Internet of Things approach. That makes this technology very suitable for temporary installation. So if you want to test just one part of the plant for revamping or repowering, or just for contract reason, you really can install without no cabling, very easy way, and you can make a testing campaign just for 1 month, a few days. So that's a very good, good option. So that's it. Thank you very much for your time, and I'm here if you have any questions or doubts.
Thank you, Marco. Very nice presentation as well. So now I will ask you to turn on your cameras and let's begin with the Q&A session. I already saw that Lucas began to answer some questions, but there's something you would like to answer live, Lucas. So please, let's begin with you while we give time for Marco to read the other questions. We cannot hear you well, Lucas. Maybe your microphone is...
Yes,
yeah.
Now it's better. Yeah.
Yes.
Thanks. So the question is, in conclusion, what is better, electroluminescence or daylight photoluminescence? And it's well, a good, difficult question. It depends on the case, I would say. So what we can say for electroluminescence, we have a slightly better image, better sharpness, because we need only one image of a PV module when it's taken during the night. We have the current injection, we have the strong signal. For the daylight photoluminescence image, we need several images, and then we have to do a precise overlapping of all the images to do the averaging and the subtraction. Therefore, the sharpness for electroluminescence is slightly higher. But then another aspect is for electroluminescence, we have to inject power, which again, yeah, the power has to come from somewhere, so it costs some money. On the other hand, for daylight photoluminescence, we do the toggling between the operating points during the day. Therefore, we have a slight loss in the in production, because in open circuit we don't produce, we miss the production of the energy. That's why I emphasized also during the presentation that it's possible for both developments to actually choose single MPPTs of the inverter to perform electroluminescence or daylight photoluminescence. Yeah, so you can go during the inspection PV module string, do it PV module string by PV module string, and you don't have to back power or reduce the production of a large share of the PV plant. Advantage of daylight photoluminescence is it can be done during the day. It is slightly slower. And then lastly, we have to talk about the applicability at the moment. So there's one thing to talk about, can we do it in the future if we have electroluminescence and daylight photoluminescence ready inverter installed everywhere, and the other one to do it nowadays. And there, well, electroluminescence is can be done everywhere by a power supply unit. Then daylight photoluminescence, there are similar devices which can be connected to the strings. But yeah, that doesn't that decreases the total speed. All of this considered, I would say it's nice to be able to do both. So especially when nowadays where there are not so many O&M companies offering luminescence inspections of PV plants, often they travel quite far, and then both depends a bit on the weather. For daylight photoluminescence, you need to have a certain radiance. So it's nice to travel somewhere and then be able to do the inspection, well, no matter what. Let's say if it's raining, you cannot fly the drone, but you could do, if there is enough radiance, you can do daylight photoluminescence during the day and electroluminescence during the night, or you just do the electroluminescence during the night. I hope that answers kind of the question. I know it's maybe not that satisfying. Yeah.
Thank you, Lucas. In the meantime, more questions came about EL and PL. Is there a minimum level of irradiation to undertake daylight?
Yes, it is. Well, from at the Technical University of Norway, they showed daylight photoluminescence for down to 50 watts per square meter radiance, so very low radiation. The thing is, then you get results which are comparable to low current injection for electroluminescence. So it is doable, but then you see, more shunt resistance and not so much single cracks and defects. So we perform it usually with 300, 400 watts or more. Watts per square meter, obviously. Yeah.
Let's take now 2 more questions on Lucas' presentation. Then let's move on to Marco's questions, and then we close the session. So Lucas, I see as well a question on, well, does EL contribute to panel degradation?
No, it is a forward current you apply, so the same current flow you have as in during production. You apply currents up to a short circuit current, which the module experiences all day. As I mentioned as well, we investigated the temperature increase, which is about roughly spoken 20 to 25 degrees Celsius if we supply or inject the current for 30 minutes or more. This is also standard standard values which the PV module experiences during normal production. So to my very best knowledge, no, not at all.
There was a very interesting question you answered on the chat, but I think it's worth sharing with the audience about the use of machine learning for image processing. Could you summarize your answer here, please?
Yes, well, my main answer was that I don't really know because we didn't do it yet. The question was if there are different algorithms working better for the specific inspection techniques or the images from the different inspection techniques. But I also said that I do expect that there are much different results, or the algorithms work much better or less good for the different inspection techniques, because we are looking at very different signals and image artifacts we want to detect. So for infrared thermography, for example, we just see a hotspot is just an intensity difference in the signal in the image. Instead, if we look for or want to detect defects with electroluminescence or daylight photoluminescence, well, the first thing is again an intensity difference, but then it depends a lot on the shape or the orientation, because we also have intensity differences for, we see the single cells, we see the bus bars and so on. So there are a lot of artifacts in this image which are no defect. Therefore we have to, we have to analyze the defect in much more detail, let's say.
All right, Lucas, thank you very much. Let's now take some questions for Marco. Marco, if you are there, please turn on your camera.
Yes.
So the first one is, in regards to the proposed device-to-cloud architecture, given that the logger has an essential role in controlling and steering the inverters. Also, the inverters need to be steered by the local grid operator, which for now is via wire. How would a narrowband IoT be able to compensate for that?
Yeah, that's a very good question, because all over Europe, the distributors or the grid operators are going in this direction to control the inverters or the production of the PV plant. So I would say that probably the architecture of the system should be redesigned, reviewed, because in this case, if you use if you don't have the data logger, the gateway anymore, you need to move this software component, this control part, to the cloud as well. And then I would say that probably in this kind of real-time control systems, the narrowband is not the best option. Probably it should be better to use the 5G, because as we have seen during the presentation, it offers a very low latency, very high peak rate. So probably it can guarantee this kind of remote control. Yeah, but this is a quite new scenario, so we will see where the market will go, but probably we will see a change of the software architecture as well.
There's a question on how those IoT devices can affect the cybersecurity of a power plant.
Yeah, this is another very good one, because I mean, every device, every technology has security challenges. So for sure, IoT needs robust cybersecurity strategies, but probably the same that they are already used for the connection in the plant. You know that I think in September last year, we had a cyber attack blocking the satellite communication on the plant. So we have seen that a lot of data were missing. The maintenance teams were in difficulties because they had no visibility on the plant. So it's something that we have always fight. So IoT is in the same challenge of all other devices, I think.
Thank you, Marco. So I'd like to close the session trying to answer a comment about the value itself of the research project. It seems that we are recommending to purchase one specific inverter by one specific producer, but it's not. So the idea of the research project being funded by European money is to prove what is possible and to be the bridge from testing to commercialization. So I would also ask here the opinion of the two speakers and concerning the exploitation strategy and how would the solar sector can benefit from these results. Any of you?
Yeah, I might also comment on on how the developments can be used. So first, of course, they can be used in future PV plants where these devices are installed, which could also be produced by other inverter manufacturers. We were wondering why no one else did it before, because it's well, not a very difficult process, but we were happy to have this project Trust PV where we have actually people from the whole value chain of PV system working together and kind of support each other in their developments for the other steps. So there are, for example, there's some work done where existing inverter of different types, smart string inverters, are updated with a small hardware to allow current injection to do electroluminescence. Of course, if you have to go through a PV plant and install it on each inverter, it's much more cost efficient, not cost efficient, but much more costly than introducing it from the beginning into an inverter. Then for photoluminescence is pretty much the same. We are just toggling between two operating points. Smart string inverters nowadays are able to do IV curve sweeps and therefore to read the different or to change the operating point of the connected strings. So we did it in this project with one producer, with Huawei, but in the end, I also had shown the different publications, so also open access. Not all information are disclosed, obviously, but well, most of it, I would say.
Exactly. Most of our research has been published open access. The reports are there in our website. So I invite all the attendees to go through them.
And then also, sorry, but to get people on board or big companies on board, of course, some some, how you say it, confidentiality has to be provided as well, I would say. Otherwise, we cannot work with industry together.
Exactly. Okay, then, so I think we can close here. All the unanswered questions will be separately. I will ask the speakers to reach out to the attendees. Thank you all again for your time, for your questions. I hope it was useful to just give you some insights on the big project, which is Trust PV. Please stay tuned. There will be more webinars. Go to our website, go through the deliverables and the open access research already there. So
thank you very much.
Thank you again to the speakers. and have a
Thank
nice
you.
day.
Bye.
Goodbye.